Safarani del Politecnico di Torino.
Thank you so much for the presentation. Allow me to speak in English because my professional academic Italian not very well. Ladies and gentlemen, good afternoon. I'm here to present our research conducted in Politecnico di Torino under the supervision of Professor Francesco Tondolo, highlighting the key aspects of our research and its significance in lightweight steel structures field. As you may know, there is a high demand for efficient and sustainable structures to help cope with global environmental, social, and economical problems. For this reason, lightweight steel framing and modular constructions as conform steel applications getting increased in these days. The most structural system used in this application is conform steel pressed frames and moment resisting conform steel moment resisting frames. However, conform steel breast frame systems, the structural performance of these systems is limited compared to conform steel moment resisting systems. Since it's good for low to mid-rise building, while conform steel moment resisting systems, that is a brand new topic for the development of lateral load resisting system suitable for high-rise building. I'm going to briefly introduce you to this, to the background of our study. Here on the left side, you can see one of the most interesting advancement in the field of conform steel moment resisting system. It's a beam column connection using a beam curved flange section. It was found that by increasing the bends on the flange, on the beam section flanges, we can improve and enhance the elastic and inelastic characteristic of the joint. Thus, we can delay local buckling and also have a joint with higher stiffness and strength and ductility. This connection was tested experimentally and numerically under both monotonic and cyclic loading. However, it might be difficult to manufacture it, and it might be difficult to place the flooring system. For this reason, as you can see on the right, an alternative section, folded flange beam section, was proposed to overcome these restrictions. And in our study, our aim is to study this connection with folded flange beam section under cyclic loading condition. For this reason, we built our numerical model, as you can see, starting from the beam column connection with folded from flange beam section. We called it type A in red. We validated our results against previous numerical and experimental research. Then we built our model with folded flange beam section. We called it type F in blue, and we studied this connection under cyclic loading conditions. We evaluated the performance of this connection in comparison with the connection with the curved flange beam section. The modeling has been carried out using Abacus software. The modeling steps include geometry, material, bolts, loading boundary conditions, mesh analysis, and the type of analysis. I'm going to guide you through this whole modeling steps in the following slides. Starting from the geometry, on the top left side of the slide, we can see the general specification of these numerical models. In general, we have two main type of models. We have type A and type F. Type A, we used curved flange beam section. Type F, we use folded flange cross section. Each model, each type, we have 3 different configurations of stiffeners. We have the first configuration without any stiffening at the connection zone, the second one with partial stiffening in the connection zone, the third one with horizontal and vertical stiffeners at the connection zone. You can see here on the bottom left side a 3D representation of type A model. Here is the 3D representation of F models with also the through blade dimension and bolts arrangement. Now we move to material, nonlinear, elastic plastic, stress strain material law was incorporated into Abacus using the experimental data from coupon test conducted in a previous experimental test. The bolts were modeled as point-based fasteners with rigid multi-point constraints. Geometrical imperfection has been considered in the model. The analysis type was general static using shell quadratic element with mesh size 10 by 10. On the right side, you can, on the top, you can see also the loading and boundary conditions. The loading was by imposing a displacement at the tip of the beam using the cyclic loading protocol on the bottom side, as shown on the bottom side on the slide. Now we can move to model validation and discuss the model validation. The model validation was carried out on type A models. In these graphs, there are, we can see its moment rotation graphs. Our results on this study of this model is represented by a green line, while the red line is the previous numerical results. The blue dotted line is the previous experimental results. We can notice that our results fits good with at least the previous numerical results, while we have a light discrepancy in specimen A2 with respect to the previous experimental results, and this calls for an experimental investigation to understand this discrepancy, and I'm going to comment on this at the end of presentation. After that, we can now go to discuss our results for the model with type F model, taking into account failure shape, strength, and the seismic behavior of this connection. Starting with failure shape here, shapes here, you can see the failure shape extracted from Abacus. If we want to comment and do a comparison, we can see the yellow circles show that F1, F2 models have similar behavior with A1, A2, and the failure here occurred in the web location at the edge of the gusset plate. However, for F3 and A3, the buckling was delayed, and the failure occurred on the flanges outside the connection zone. Moving to the strength discussion, we extracted the moment rotation curves for all models, and to comment on that, we can see that for F1, F3, the strength degradation due to cyclic action is slightly higher than A1, A3, while the contrary for F2, A2. In general, we can see that the capacity of type F models is almost similar to A-type model. The last step is we studied also the seismic behavior of this connection, but I'm gonna briefly guide you through the procedure. So first, for each cyclic curve, we extracted the backbone curve, and we identified 4 points, A, B, C, and D. A for yielding, B the peak, C ultimate, and D is the failure point. Then we bilinearized the backbone curve, and at the end we could compute ductility and energy dissipation capacity. Ductility is the ratio between the ultimate rotation with respect to the yielding, while energy dissipation is the area under the bilinearized curve. Here you can see a discussion, slight comparison between type A models and type F models in terms of ductility and energy dissipation capacity. We noticed that we have slight difference between both connection, and in general we can notice that the seismic behavior of type F model is similar to type A model. And this leads us to the conclusion where we can find that lightweight steel framing are efficient system. They can help us to overcome the global challenges, and this connection with folded flange B section can be a good alternative to the connection with curved flange beam section, as it has the similar behavior in terms of strength and seismic behavior, and at the same time it can overcome the constraint in terms of practical practice and manufacturing. At the end, experimental tests are needed to further investigate this kind of connection and to extend our database. And here in Politecnico di Torino, we are planning an experimental campaign to further contribute in this field. At the end, thank you so much.
Thank you for your presentation.